An 11% voltage drop at startup, equivalent to a voltage reduction of 120 volts assuming a 1100 volt supply, is significant. This voltage drop can lead to reduced motor torque, making it difficult for the pump to deliver the required fire flow. Fire pumps require high torque at startup to overcome the static inertia of the pump and deliver the necessary flow and pressure. Reduced torque due to voltage drop can result in the pump failing to meet its performance requirements. Here are a few mitigation measures. Firstly, consider increasing the feeder cable size to reduce voltage drop. This will provide the motor with higher voltage at startup, improving torque availability. Secondly, explore options for reducing the motor's startup current, such as using a soft starter or a reduced voltage starter. This will minimize the voltage drop during startup. Thirdly, install a voltage regulator at the motor location to maintain a consistent voltage supply throughout the startup process. Also, perform comprehensive tests and commissioning to verify that the motor has sufficient torque to meet the fire pump requirements, even with the expected voltage drop. There are some additional considerations as well. Ensure that the feeder size complies with NEC requirements for voltage drop under normal and emergency operating conditions. Adhere to applicable codes and standards such as NFPA 20 and IE 141, which provide guidance on fire pump power systems. Consult with the motor manufacturer to determine the impact of voltage drop on motor performance. They can provide recommendations and guidance on acceptable levels of voltage drop. Addressing the excessive voltage drop during motor startup is crucial to ensure that the fire pump can deliver the required performance. By implementing appropriate mitigation measures, you can confidently protect your facility's fire safety system. A deeper dive into the NEC requirements is worthwhile. The NEC addresses voltage drop in several sections, providing guidance on conductor sizing to minimize voltage drop and ensure proper operation of electrical equipment. While the NEC doesn't mandate a specific voltage drop percentage, it recommends limiting voltage drop to ensure efficient operation. For feeders, a maximum voltage drop of 3% is recommended, and for the combined feeder and branch circuit, a maximum of 5% is recommended. These recommendations are found in informational notes within the NEC, specifically in sections like 210.19, A1 and 215.2, A1. It's important to note that these are recommendations, not mandatory requirements, but they serve as a good practice for designing electrical systems. The NEC also addresses voltage drop indirectly through requirements for conductor sizing. For example, Section 430.22 requires conductors supplying motors to have an ampacity of not less than 125% of the motor's full load current. This oversizing helps to reduce voltage drop, especially during motor starting. For fire pumps specifically, NEC Section 695 provides additional requirements. While it doesn't explicitly state a maximum voltage drop percentage, it emphasizes the need for a reliable power supply to ensure the fire pump operates effectively during emergencies. This implies that voltage drop should be minimized to the extent necessary to ensure proper pump operation. Several factors influence voltage drop in a feeder. These include the feeder length, the conductor size and material, the current flowing through the conductor, the power factor of the load. Longer feeders will experience greater voltage drop due to the increased resistance of the conductor. Larger conductors have lower resistance, which reduces voltage drop. Copper conductors have lower resistance than aluminum conductors, resulting in less voltage drop for the same size conductor and current. Higher current flow leads to increased voltage drop due to the increased voltage drop across the conductor's resistance. Loads with lower power factors, such as inductive loads, will cause greater voltage drop than loads with higher power factors. There are several methods to calculate voltage drop in a feeder. The most common method is to use the following formula. Voltage drop equals current times resistance times length divided by 1000. Where voltage drop is the voltage drop in volts, current is the current flowing through the conductor in amps, resistance is the resistance of the conductor in ohms per 1000 feet, and length is the one-way length of the feeder in feet. This formula provides an approximate voltage drop calculation for alternating current circuits. For more accurate calculations, especially for long feeders or feeders with significant inductive reactance, it may be necessary to use more complex formulas that take into account the conductor's impedance and the power factor of the load. Mitigation methods also help reduce voltage drop. Increasing the conductor size is one way to reduce voltage drop. Using copper conductors instead of aluminum conductors will also help. Reducing the feeder length by relocating the power source closer to the load reduces voltage drop. Improving the power factor of the load by using power factor correction capacitors can also help. Using a separate feeder for the fire pump can isolate it from other loads, minimizing voltage drop during pump startup. Other considerations are important as well. The acceptable voltage drop for a fire pump depends on the motor's design and the pump's performance requirements. Consult with the motor and pump manufacturers to determine the acceptable voltage drop limits. Voltage drop can affect motor torque, motor starting time, and motor temperature. Excessive voltage drop can reduce motor torque, making it difficult for the pump to start and deliver the required flow. It can also increase the motor starting time, which can be critical in emergency situations. The heat can cause the motor to overheat and fail. It's important to consider voltage drop under both normal and emergency operating conditions. During normal operation, voltage drop should be within acceptable limits to ensure efficient operation of the fire pump. During emergency operation, voltage drop should be minimized to ensure reliable pump operation. Fire pump installations often require coordination with the local utility company. The utility company may have specific requirements for the power supplied to fire pumps, including voltage drop limits. Conducting a voltage drop study is recommended to determine the voltage drop under various operating conditions. This study should consider the feeder length, conductor size, load current, and power factor. The results of the voltage drop study can be used to determine if mitigation measures are necessary. When selecting a reduced voltage starter, several factors should be considered, including the type of motor, the load characteristics, and the desired starting torque. Autotransformer starters provide high starting torque and are suitable for applications with high inertia loads. Pot winding starters are less expensive than autotransformer starters but provide lower starting torque. Solid-state starters offer smooth, stepper starting and can be adjusted to provide the desired starting torque. When installing a voltage regulator, it's important to select a regulator with sufficient capacity to handle the fire pump starting current. The regulator should also be located as close as possible to the motor to minimize voltage drop. Testing and commissioning are essential to verify that the fire pump meets its performance requirements, even with the expected voltage drop. These tests should include a full flow test to verify that the pump can deliver the required flow and pressure. A starting voltage test should be done to verify that the motor has sufficient torque to start and accelerate the pump to full speed. The NEC mandates specific requirements for fire pump feeders to ensure reliability and safety. Section 695.6 specifies that the fire pump feeder shall be sized to carry 125% of the fire pump motor's full load current, as well as the sum of the associated equipment. This ensures the feeder has sufficient capacity to handle the pump's current and any additional loads. According to 695.6 (1) The disconnecting means for the fire pump motor must be lockable in the on position to prevent accidental disconnection during a fire emergency. This ensures the pump remains operational when needed most. NEC 695.12 These states fire pump feeders must be physically routed outside buildings where possible, or encased in 2-inch concrete or brick if routed within a building to protect them from fire damage. The installation methods of wiring for fire pumps must comply with NEC 700.9 (1) These wiring methods provide a high degree of fire protection to ensure circuit integrity. NFPA 20, the standard for the installation of stationary fire pumps for fire protection, also offers crucial guidelines. NFPA 20 outlines specific requirements for the location and protection of fire pump controllers, including the need for a dedicated room or enclosure. This helps protect the controller from damage and ensures its reliable operation. The standard also specifies requirements for the fire pump's power supply, including the need for a reliable and independent power source. This ensures the pump can operate even if the normal power supply is interrupted. It is important to consult with the motor manufacturer to determine the motor's voltage tolerance and its impact on motor performance. Understanding these limits is crucial for ensuring the fire pump operates reliably and meets its performance requirements. Motor manufacturers can provide valuable insights into the motor's performance characteristics, including its torque speed curve and its ability to withstand voltage variations. This information can help determine the acceptable voltage drop limits for the fire pump installation. Furthermore, reduced voltage starting methods like soft starters or auto transformers can significantly reduce the inrush current during motor startup, thereby minimizing voltage drop. These starting methods gradually increase the voltage applied to the motor, reducing the mechanical stress and electrical disturbances. Soft starters use solid-state devices to control the voltage applied to the motor, providing a smooth and stepless start. Auto transformers use a transformer to reduce the voltage applied to the motor during startup, gradually increasing the voltage as the motor accelerates. Also, consider the impact of ambient temperature on conductor ampacity. High ambient temperatures can reduce the ampacity of conductors, which can increase voltage drop. It may be necessary to upsize the conductors to compensate for the effects of ambient temperature. The directing factors for ambient temperature are provided in NEC Table 310.15. 8.2. 8. The power factor affects the amount of current drawn by the motor. A low power factor can increase the current, leading to higher voltage drop. Installing power factor correction capacitors can improve the power factor and reduce voltage drop. The NEC provides guidelines for power factor correction in Article 460. It's also important to consider the available fault current at the fire pump's power source. The fault current affects the selection of overcurrent protection devices and the withstand rating of electrical equipment. A higher fault current may require the use of equipment with higher withstand ratings to prevent damage during a fault. When designing a fire pump system, consider the life cycle costs of different design options. While some options may have higher initial costs, they may result in lower operating costs and improved reliability over the long term. This includes factors such as energy consumption, maintenance costs, and equipment replacement costs. Reviewing single-line diagrams are a very important step. They provide a visual representation of the electrical system, including the fire pump, its power source, and all associated equipment. A single-line diagram helps identify potential voltage drop issues and ensures that all components are properly sized and coordinated. The single-line diagram should include the conductor sizes, lengths, and materials, as well as the ratings of all overcurrent protection devices. Be sure to check the feeder conduit fill. Overfilled conduits can lead to overheating and reduce conductor ampacity. The NEC specifies the maximum allowable conduit fill in Chapter 9, Table 1. Following these guidelines ensures adequate ventilation and prevents overheating. Always consider harmonic distortion. Harmonic currents can increase voltage drop and cause overheating of electrical equipment. Harmonic filters can be used to reduce harmonic distortion and improve the performance of the electrical system. Regular maintenance is essential for ensuring the long-term reliability of the fire pump system. Maintenance activities should include inspecting and testing the electrical equipment, including the feeder conductors, overcurrent protection devices, and motor starters. Maintenance should also include cleaning the equipment to remove dirt and debris. There are more codes and standards to adhere to. IEE 141, Recommended Practice for Electric Power Distribution for Industrial Plants, provides guidance on designing and operating electrical power systems in industrial facilities. This standard covers a wide range of topics, including voltage drop, power factor correction, and harmonic distortion. It also provides recommendations for selecting and installing electrical equipment. Another one is IEE 493, Recommended Practice for the Design of Reliable Industrial and Commercial Power Systems, provides guidance on designing reliable power systems for industrial and commercial facilities. This standard covers topics such as redundancy, backup power, and surge protection. It also provides recommendations for minimizing downtime and ensuring the continuity of operations. This includes specific voltage requirements to consult with the local authority having jurisdiction. The authority having jurisdiction may have additional requirements for fire pump installations, including voltage drop limits and testing procedures. Consulting with the authority having jurisdiction early in the design process can help ensure that the installation complies with all applicable requirements. It's also crucial to document all calculations and design decisions. Proper documentation is essential for future reference and for troubleshooting any problems that may arise. The documentation should include the voltage drop calculations, the conductor sizing calculations, and the equipment ratings. It should also include a copy of the single line diagram and any other relevant information.